Hi, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. This time we are finally getting to the most massive, most compact, most bizarre objects in the universe, black holes. Black holes are the final triumph of gravity over all the matter or any matter. They're the end states of the cosmos, and they are the horizons into nothingness. So what's really interesting about them is everything. So let's see what they are. Back in 1783, a scientist and clergyman named John Michell looked at Newton's ideas of the nature of what gravity was, and he also looked at Newton's ideas concerning corpuscular light. We talked about that in an earlier lecture, the corpuscular nature of light that Newton came up with. Well, John Michell took that seriously and said, well, if light is made of particles, then it has to have energy in order to fly up out of something. So imagine that you actually toss something up, but it came back down. So if light's a particle, then presumably you could make something where the escape speed is greater than the speed of light. And since in 1783 they had a pretty good idea about what the speed of light was, then they could find. He stated in his speech at the Royal Society of London in November 1783 that if you took something that was the same mass and density of the sun, but made the sun 500 times bigger with the same density that currently is, then light could not exit from the sun. And that's really interesting. You could all light from such a body would be made to return to it by its own proper gravity, which is fascinating. So John Michell came up with the concept of what he called dark stars, which is a really cool way of talking. Then in 1796, Pierre-Simon de Laplace, who is one of the more famous mathematicians of the 18th century, and in fact one of the most famous mathematicians of history, discovered that mathematically there really actually could be stars whose gravitational field could be strong enough such that the escape speed would be the speed of light. The other was a consideration, but this is a mathematical proof. Then it took a long time before Carl Schwarzschild in December of 1915 looked at Einstein's equations of general relativity and actually made the first solution to Einstein's field equations. And the field equations describe the relationship between the curvature of space-time and the matter and energy embedded in that space-time. And so what he did is he said, okay, let's keep it really simple, make it spherically symmetric, make it non-rotating, make it static, and put that spherically symmetric matter in one place with nothing else left in the entire universe. And he created the way to measure space-time around such an object, the Schwarzschild solution to the Einstein field equations, which is shown in that little equation below. But what he did is he actually wrote this thing while he was serving in the German army in World War I. And he wrote to Einstein saying, sent a letter to him and sent his notes off to Einstein. And Einstein replied and said that he thought it was a wonderful treatise and a wonderful solution to it. And he presented it in Carl Schwarzschild's name at the Academy. So so that was an amazing thing that he was able to do, because Carl Schwarzschild died about a year later from a genetic disease that developed while he was on the front, not as a result of injuries at the front, but he died shortly thereafter. So his work lives on, and the name of the thing that we think of as black holes lives on there. Then about 20 years later, J.R. Oppenheimer and Hartland Schneider, who was a graduate student at the time, in 1939, described what would happen if a star exhausted all forms of nuclear fusion and then exceeded the neutron degeneracy pressure. And so I list that thing there, and they said, well, there would be nothing to hold it up. And so that would collapse down to an infinite singularity, a black hole. So that's where the original idea comes from, because Oppenheimer himself, just earlier that year, with a couple of others, actually figured out what the neutron degeneracy support could be for a neutron star. And then they posited, and Oppenheimer and Snyder then posited what would happen if nothing could support it. And so they found that it would actually free fall all the way to a singularity as nothing left in existence below it. All right, so let's see what we know about these kinds of objects. And if we compare, say, the Earth, and initially let's go back to our study of white dwarfs. White dwarfs are these insanely dense objects that are about the mass of the sun, or thereabouts, up to 1.44 solar masses, and they're about the size of the Earth. So the gravitational pull of a white dwarf is supported by degenerate electron gas pressure. Not normal, not a solid, it's not a solid, it is not a normal gas, it's a degenerate electron gas. So the neutrons and the neutrons and protons and nuclei are buzzing around just like normal, but the electrons are all stacked in their lowest possible energy states, and there's no way to compress the gas. So if you add more mass to a degenerate electron gas, the actual white dwarf gets smaller. So remember we said that a degenerate electron gas has a maximum mass of 1.44 solar masses, the Chandrasekhar limit, and that dictates whether or not a white dwarf can exist above that mass. However, in the throes of a huge explosion, a neutron star can be formed in a type 2 supernova, and that can exceed the Chandrasekhar limit and compress the electrons and protons together to form a neutron star. And the neutron star can be between, say, about one solar mass up to about 3 or so solar masses, and those things then support by neutron degeneracy. So the neutrons, well, we wouldn't really think of it so much as a gas, because when we studied neutron stars, we learned that, well, they're very odd things. They're not really we wouldn't think of them as a gas. They're harder than any possible solid, even though they behave in certain ways as a gas. Mostly they behave like a superfluid, and the states of matter of a neutron degenerate gas isn't really gaseous in a way. So, but in any event, it supports against the pull of gravity. So that's one pressure that can push back against gravity, is neutron degeneracy. However, if the star that creates a type 2 supernova is more massive than about 18 solar masses, then that would create a supernova that would create a core larger than about 2.5 or 3 solar masses, and neutron degeneracy would not be able to support that against that pressure, against that pull of gravity inside such a small thing that's only about 10 kilometers across. If it exceeds about 3 solar masses, it will collapse, and it will collapse down inside. Oppenheimer and Snyder found that there's nothing that would stop the collapse. Absolutely nothing is known to physics. And in fact, what's even weirder is that it is known that from general relativity that pressure itself is an energy density. And so as the pressure rises, the pressure itself contributes to the energy density and then further hastens the collapse. So even if there were another version of pressure, it would contribute to the collapse itself. So therefore, anything more massive than about 2.5 solar masses inside of a small radius, such as about 10 kilometers, there is nothing that can support it. The core of the star collapses to a singularity, and it becomes a black hole. So this is really interesting. It's got this kind of, what is a black hole? Well, it's not a hole so much as anything. Well, we're going to describe what these things are. But a black hole is actually we can think of that white ring that we see in this image as a surface. And that surface has a very special feature. And we're going to see what that surface is shortly. But first let's revisit the concept of escape speed. Remember, right in the beginning from 1783, people said, well, if something had the escape speed, the speed of light, then light couldn't leave. So let's look at what that means. Well, we can think of the kinetic energy, which is that 1/2 mv squared for some mass. The faster it's going, m, some mass, the v is the speed, then it gives you the kinetic energy of it. But if that's equal to the gravitational potential energy, we say, if it's just equal, the amount of kinetic energy of a particle is just equal to the gravitational potential energy of that particle, which is, say, the Earth, which is the capital M, times the mass, maybe it's like a gas particle or a rocket or anything, divided by the radius from the center of mass, or the distance between those two centers of mass. If we equate those two things and solve for the v, we get what's called the escape speed. And that is how fast an object must go such that its kinetic energy exceeds the gravitational potential energy, meaning how much energy it is by falling. And for the Earth, if you plug in for the mass of the Earth and the radius of the Earth, you get an escape speed of about 11 kilometers per second. So that's pretty fast. So if you want to escape the Earth and never fall back down, you get so much energy that you exceed the gravitational potential energy and never fall back, you've got to go 11 kilometers per second. That's really fast. The average person can run, the average really good athlete can run a 10 kilometer, or the average person can run a 10 kilometer road race in maybe an hour or so. Elite runners can run it in, say, 20, 25 minutes. But for the Earth, if you want to get away from it, you got to go 10 kilometers in 1 second. So that's about 11 kilometers in 1 second, which is the equivalent of going around the outer loop of Central Park in 1 second, which is really fast. So that's how fast you got to go in order to escape from the Earth. So let's see what happens if you shrank the Earth. So currently, if you went just 10 kilometers per second, you go up very, 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 very high, and eventually you'd fall back down. If you're going slower than 11 kilometers per second, you're going to fall back down eventually. But if you go faster than 11 kilometers per second, you will eventually you will escape from the Earth. Now, if you shrank the Earth, kept the Earth's mass the same, you just compressed it, and you pushed the Earth down 100 times smaller, so that it was 65 kilometers across, then the escape speed would be 110 kilometers per second, because it goes as the square root of the radius. But if we then said, fine, what do we got to do in order to make the escape speed 300,000 kilometers per second? And that means you got to shrink the Earth down to about 1/3 of an inch, or a few millimeters. That's really small, smaller than a centimeter, about the width of your pinky nail. So if you took the Earth, the entire Earth, which is over 12,000 kilometers across, and compressed it to smaller than your pinky nail, then the escape speed would be the speed of light. That's a pretty incredible compression ratio. And so what's going to do that? Well, a supernova can do that. So what is a black hole? It's the extreme ultimate object. The gravity, therefore, is so strong that nothing, not even light, can escape. And any infalling matter, something that falls into a black hole, gets totally torn apart by tidal forces that basically mean that the gravitational pull between, say, the top and bottom of something gets pulled apart. That's the tidal forces of it. And the escape speed escapes the speed of light. And it's a black hole because it's the surface of the black hole, whatever that is, we don't even know what that really means yet. But that surface, we're just going to say that for right now, if the escape speed is the speed of light, then light can't get out. So therefore it would be black. And it's a hole because, well, nothing goes faster than the speed of light, so therefore anything that goes in doesn't come out. So that's why it's a black hole. And let's talk about that surface for a little bit. It's a very odd thing. We're going to call that radius, that special radius, the Schwarzschild radius, which derives from Karl Schwarzschild's metric, the way you measure space and time near a spherically symmetric object. And we'll measure that to say that since light cannot escape a black hole, if it comes closer than a radius, that's called the Schwarzschild radius. And that if it gets inside that Schwarzschild radius, it will fall to the singularity no matter what. And so if we look at R sub s, which is the definition of the Schwarzschild radius, it's 2 times the gravitational constant times the mass of the object divided by the speed of light squared. So all you have to say is that, wow, you can take whatever mass it is. It doesn't matter what the mass is. It can be an Earth-sized mass. It can be a sun. It can be, say, 1,000,000 solar masses. Then you can derive what the Schwarzschild radius is. So something like the sun is about 3 kilometers across. So if you have a black hole that has the mass of 1 solar mass, the size of the Schwarzschild radius, the radius of the black hole, is 3 kilometers. And if you look at a white dwarf, the white dwarf has a radius of about the size of the Earth, which is about 6,000 kilometers. And if a neutron star is about 10 kilometers. So the size of a black hole is really not that much smaller than a neutron star. So neutron stars are just on the boundary of being, of compressing inside their Schwarzschild radii. That's why they're such extreme states of matter that we saw in the previous lecture. All right, so now let's take a look at what the relative sizes of a black hole are, and we're going to do it by a size scale comparison. So here's the size of the sun, and this is a beautiful image taken in visible light of the sun, actually an ultraviolet light of the sun, and we see a beautiful prominence from the sun reaching out. And I've put the Earth underneath the prominence for correct scaling, because remember the Earth is about 100 Earths can fit across the sun, so that's about right for the size of the Earth compared to the size of the sun. It's actually that pixel's a little too large because we need 100 to fit across there, and it seems like we get less than 100 if we use that one, so it's going to be a little smaller than that. But let's zoom in anyway. And we see there's the size of the Earth with respect to this prominence, which is a typical large prominence on the sun. And now we zoom in onto the Earth and we go all the way down to, say, Florida. We look at Florida and we zoom into Florida and we keep zooming in and something is appearing and we're looking at a particular area in Florida and we zoom into that area and we find a black circle. The size of a black hole, the mass of the sun. So we take that entire thing of the sun and compress it down to this big, which is just about the size of Cape Canaveral Air Force Station, which is where they launch all of the rockets from. That's the launch pads you see around it. And there's the landing strip that the space shuttle used, as well as other planes and aircraft that come in for a landing. But all of those launch pads are the great launch pads for the Apollo missions, as well as the space shuttle and many other things. But if we look at the size of the black hole, it's really small. It's only a few kilometers across. That thing's small, you take all of the sun and compress it down to that. Now, of course, if you put it right next to the Cape Canaveral would no longer exist because it would be torn apart by the incredible tidal forces that would shred the Earth immediately. But that's just to give you a sense of scale. So now we're going to use a new word, a new definition. It's called the event horizon. The Schwarzschild radius defines what we mean by what's called the event horizon, and that event horizon surrounds the black hole's singularity. Anything occurring inside the event horizon, inside the Schwarzschild radius, is invisible to the outside universe because light can't get out from inside the Schwarzschild radius because it has to go faster than the speed of light to get out, so you can't. So no events happening inside the Schwarzschild radius can be seen. So this is an effective horizon. In fact, it is a horizon. Horizons are things you can't see over and around, right? That's kind of the definition of the horizon. Things are past the horizon, they are over the edge of the curvature of the Earth, so you can't see them. And that's what we mean by a horizon. And so the horizon is just the place where we cannot see anything from below there. Anything closer to the singularity than the Schwarzschild radius never leaves the black hole, can't come out, there's nothing it can do, nothing ever comes out, I don't care what anybody says, it's a lot of fun to say, you're going to find all sorts of silly speculation everywhere. It doesn't happen, that's the nature of an event horizon in a Schwarzschild radius. So that's what we call the event horizon. The event horizon is also the surface that black surface. It has a radius of the Schwarzschild radius. And that's not really a surface. There is nothing there. That's weird. No, we think of it as, oh, what's on the event horizon? Well, there is nothing on the event horizon. That's just the place from which light cannot escape. So it is black. There's nothing there. It's inside of there is the singularity, but we cannot see anything from there. No events can be seen from inside of there. And that surface is a mathematical construction, and it only exists because, well, you just can't see it. So that's what we call the event horizon. Gravity around black holes is insanely intense. However, if you're far from the black hole, let's say a one solar mass black hole, if the Earth was orbiting 1 astronomical unit away from a 1 solar mass black hole, the only difference would be, well, there might be some X-rays as stuff falls in, and it would be certainly there would be no sunlight, but we would orbit. The Earth would orbit that black hole. So the only effects that happen are when you're very close to the black hole, when the radius of your orbit is less than about 3 Schwarzschild radius, then there's no stable orbits, which is kind of funny to think. We can think of stable orbits getting very close to the sun, but once you're inside 3 times the Schwarzschild radius, there are no stable orbits and things just fall in. That's one of the strange things that occurs inside of the dynamics due to the Schwarzschild metric. So mass would definitely fall in, but at 1.5 times the Schwarzschild radius, or look at that disk there and just take half the radius and push it out again, and that's where that Einstein kind of golden ring is, that pinkish ring is around. is that photons or light would orbit in a circle, and they can't get away. So if light was orbiting there, it would be like this glow of light that simply can't leave. So if you happen to fall through that, you'd see a bright light as things hit you in the face. But you would never actually see anything escape from there. And so the photon, if a photon could go up and it could go down, mostly down, but inside 3 Schwarzschild radius, all normal matter falls straight in. All right. So why does this happen? And we're going to discuss some really very interesting concepts associated with black holes in just a little bit. But we talked about general relativity in a previous lecture in the series, and we discussed the concept of the equivalence principle. And the equivalence principle is Einstein's great insight into the nature of space and time. And he simply said that all physical laws are the same, no matter how the laboratories in which they are measured move with respect to each other. So if you're on the surface of the Earth, you're going to have the same physical laws as someone that's in a rocket, accelerating upwards at the same exact acceleration as someone standing on the surface of the Earth. So you can't tell whether you're in a boxed room on the surface of the Earth or in a rocket accelerating upwards at 1g acceleration. Likewise, there's no way to tell if you're floating freely in space in a box and falling towards the Earth freely in a box. There's no way to tell the difference between them. However, there are definite differences between these two things as seen from outside observers. And also in the bottom pair show freely falling. The others show not freely falling, but accelerated frames. In fact, you could even look at the one on the lower right as an accelerated frame as well, but it's freely falling with respect to the observer who's falling. The equivalence principle says that all physical laws are the same for all laboratories, and if you wish to understand how things are slightly different, then you simply must take into account the fact that there's curvature of space-time, which affects how you measure what you're seeing in someone else's laboratory. But inside your own laboratory, no matter where you are, you measure all the same physical laws. That's how that works. It leads to some very strange constructions. But let's just kind of put those words out here to really demonstrate what I mean. And the equivalence principle really means that everything, quantum mechanics, electrodynamics, mechanics, all sorts of things, thermodynamics, all of them are the same for all inertial observers, no matter what. If you're in free fall, or floating, or standing still, or moving with a uniform speed, or even falling in a uniform gravitational field, there's no way to tell any of these things apart using any known physical law. That's incredibly important, because that means that general relativity, which is a description of gravity, says that gravity itself is a fundamental interaction that's relative to the observer. So that's what we mean. It's not a physical law in of itself, like quantum mechanics or electrodynamics or thermodynamics. It is a fundamental interaction that's relative to what you're observing. So Newtonian gravity can then be said, okay, Newtonian gravity, like we talked, F equals gmm over r squared, right? Keep that old Newtonian gravity dance. And you can restate it not as a force. So now we think of it as not as a force due to gravity, but rather a curvature of space-time. So space-time is curved, and so therefore things fall according to the curvature of the space-time in which they exist. There's no force. Everything's just following the lay of the land. And so far, general relativity has survived extraordinarily stringent tests, and there's been amazing tests that we'll talk about when we talk about gravitational waves that even provide even greater tests for general relativity. And there are other tests as well that seem to say that so far, general relativity is the most correct description of gravity, because right now it has very testable predictions, and those tests and the predictions from those tests have been supported. So what's it like falling into a black hole? All right, let's pretend we got 2 astronauts, and there's one astronaut inside a rocket, and then that rocket, and her name is Jill, and she hangs out in the rocket, and her friend Jack is going to go fall down the hill. And so Jack gets out and gets in a separate little box in a spacesuit, And what he's going to do is he's going to fall towards the black hole. And he's got a laser, and the laser's blue, and he shoots it at Jill, and Jill says, okay, just hit the target. Don't hit my face with that thing. That's really irritating. So he then falls towards the black hole, shooting the laser in pulses. Every second he goes pulse, 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 pulse. And it's a blue laser pulsing every second or so. Let's call it a second just for fun. And what she's going to do is watch him fall in. Now, this is going to be kind of the end of their relationship, as we're going to see very soon, because this is going to be kind of the end for Jack. Well, let's see what happens as he falls into the black hole. So he falls in a bit more. From his point of view, he's just seeing the ship getting further away, and Jill sees him getting further away as well. And so he continues to flash the blue laser once a second, according to his watch. So he's got a timer. And on that timer flashes the thing once a second. That's what he's going to do for as long as he can. From Jill's point of view, she's seeing something strange. She sees it take longer and longer for the laser pulses in between each individual pulse. It's taking longer and longer for them to arrive. And every pulse that he sends as he's falling, each successive pulse has a longer wavelength. It becomes redder and it becomes fainter. It's losing energy, it's losing intensity, and the time interval between them is stretching, and it's going to longer wavelength and lower energy. Furthermore, as Jack further falls, he sees the outside world getting stranger and stranger. He sees the outside world become wildly distorted. Stars are changing position around him. He starts to see proper motion of the stars moving very, very, very fast. Jill, however, is seeing Jack's laser flashing maybe once an hour, slower and slower in between. And the laser flashes have now, as he gets closer and closer, maybe the laser flashes have been redshifted so very strongly that now she has to dial her frequency down to AM radio in order to actually to see the flashes. So now she no longer sees them. She's getting them in radio frequencies, and they're getting fainter and fainter. So if he started off with a really dim laser, she's not going to see it. Finally, he gets to the event horizon, and when Jack gets to the event horizon, she sees that the laser, there's one last pulse, and then another one maybe months or years later, maybe even never. And the next one never comes. So for her, she never sees the last pulse. And the very last one is extraordinarily faint. Maybe she had to dial up her receiver, put a gain on it, massive gain on it, build a huge antenna to try to receive the light. And it's extraordinarily long wavelengths, maybe tens of kilometers or hundreds of kilometers long. And she never sees another flash from Jack. But Jack doesn't know. He doesn't see this. Remember, for him, all laws of physics are the same. And that's what the equivalence principle says. So as he's falling, he's still ticking away one second at a time. Tick, 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 tick. That's what he's doing. And he's shooting a blue laser. So that's what he sees. The only problem is, as he crosses the event horizon, he feels some pretty strong tidal forces as his feet get ripped away from his ankles, get ripped away from his knees, get ripped away from his waist. Everything gets shredded and pulled apart, and eventually his eyeballs get pulled into pieces and bits. And it's just kind of bad for Jack. So it wasn't a very good fall for him. He might have fallen maybe an hour, maybe 15 minutes or something like that. But in the last few seconds, he had a big problem. And once he gets inside the singularity, well, whatever is left of him, whatever could possibly be left of him, immediately falls down to the center of the black hole, at the center of it, and gets crushed to infinite density in the singularity down in the center of the black hole, which is a very weird place down in the singularity, which is the point of no return. So let's see what some of these effects are that Jack and Jill experienced. One of the important effects is called gravitational redshift. And gravitational redshift is the redshift due to a photon climbing out of a strong gravitational field. So if you're at the roughly outside a black hole of about one solar mass, which is about 3 kilometers in diameter, then if you at about from 10 kilometers above it, maybe three times the Schwarzschild radius, and you beam out, say, a visible wavelength light, By about 100 kilometers, it's been redshifted down to infrared, and by 10,000 kilometers, when it finally gets out of the gravitational field, it's been redshifted to the radio. However, X-ray light that comes from extraordinarily hot stuff that's falling right into the black hole would be redshifted down to ultraviolet and then down to visible light by the time it gets to 10,000 kilometers away. So we would expect there to be extraordinarily redshift that would occur as it comes up. So that's what these equations on the right show. Z is the redshift, lambda observed is the wavelength that we observe it to be, and lambda emitted is the emission wavelength of the light. And Z, that's the definition of redshift, is the difference between the observed and the emitted wavelengths of light compared to the emitted wavelength. And the bottom relationship shows what the wavelength that we would get if we were standing off, say, an infinite distance away compared to the emitted wavelength. So that would be observed at such a far distance that we don't feel the gravitational pull of it all, say maybe 1,000 light years or something, and that's good enough. So then we would see that the R sub S is the Schwarzschild radius, and R sub E, capital R sub E, is the radius from which the light was emitted. And you can see that if the closer it is, the closer to radius emission is to the Schwarzschild radius, R sub S, that number gets closer and closer to zero. But the reciprocal of the square root of a number that's close to zero is infinite. So the wavelength gets longer and longer and longer and longer as you emit it from closer and closer and closer to the black hole. So that's gravitational redshift. The other thing that we learned is that we heard that Jack's clock looks like it got ticked slower because he thought it was a second. His watch always shows that it's going by 1 second at a time. However, Jill saw the intervals between the pulses get larger and larger and larger. And that's because of gravitational time dilation. So Jack's clock, as he's deep in the gravitational field, compared to what Jill's sees, they're different. And Jack doesn't ever appear to ever fall through the event horizon according to Jill, because his clock gets slower and slower and slower. So from Jill's perspective, if she could somehow see Jack and see the dim, dim, dim light that's extraordinarily redshifted from him, then she would see him stop moving and never get into the event horizon, because there would be one last image of his light coming from, say, the light that reflected off of him. Instead of a laser, maybe he just shone a light on himself. That would be deeply redshifted, and it would not show him moving at all. And therefore, from Jill's perspective, he never crosses the event horizon. He just moves slower and slower and slower. Because for him to cross the event horizon, from her perspective, would take an infinite amount of time, as we can measure from that equation that's across the bottom. And T sub far is Jill's clock on board the spacecraft, far from the black hole, and T sub deep is somebody whose clock is deep in the gravitational field. And what we see in this is that if you divide the T sub deep, whatever Jack is measuring, it might be 1 second. If you say, oh, he is how far from the center of it, we see that crazy square root, that 2gm mass of the black hole divided by the radius of the black hole, radius at which Jack is emitting the light, not now the radius of the Schwarzschild radius, but R stands for where Jack's emitting the light from, and then there's a c squared there. The closer that R gets to 2gm over c squared, which is the Schwarzschild radius, the larger and larger and larger the time becomes. And in fact, that's exactly the same thing that we saw with the wavelength. So the wavelength becomes longer and longer, and the intervals of time become longer and longer, according to Jill. So you get gravitational redshift and gravitational time dilation. And also notice that the redshift indicates that the photons are losing energy as they come out, and they take longer and longer and longer to get to Jill, which is interesting. They're traveling at the speed of light, and Jill might be only 100,000 kilometers above, or above the black hole. So why doesn't the light get to her, and say, since light travels, let's say she's 300,000 kilometers above the black hole, or 1 light second, why doesn't it take a second for the light to get there? Well, that's really weird because of time dilation. All right, so let's see what it looks like as Jack falls into the black hole. So if Jack's falling into the black hole, this is what he sees. So he's going to be spiraling around the black hole. See how this image shows it kind of spiraling. So as Jack falls into the black hole, we see him getting closer and closer and closer to the black hole. Eventually, he passes through the stable orbits where you can orbit stably. We get closer and closer inside of those stable orbits. He always sees the black hole beneath him, though, which is really interesting. Remember, the light can't get up from below. Eventually, he falls through the horizon, through the event horizon, and then all the way down to the singularity itself. And here he is at the bottom now. That's rather interesting. So what we saw with that is that the black hole was always below Jack, even as he got all the way down to the center. He fell through the horizon, he always saw stars above, and he always saw the black hole below. That's what Jack saw if he could somehow stay together against these massive, massive, massive tidal forces, which of course he can't. And we see there's massive redshifting of light as it's being redshifted around him, and all the light gets stranger and stranger and more distorted as he goes. And a lot of these images that you're going to see come from Dr. Andrew Hamilton, who is at University of Colorado, who is a major black hole researcher and has looked at the mathematics of it and published numerous things and made amazing simulations. So I provided a link here, and I'll indicate on those websites where his material is. But he's done some great TED Talks. He's been featured at the World Science Festival, and these are some fantastic things. And some of his ideas aren't properly given their due, so I'm giving them their due. Now, another thing that can happen, that does happen, as they fall into a black hole, as Jack falls in, we talked about he gets ripped apart. That's called spaghettification. So as Jack falls in, he gets both squished together and stretched apart. And that's the nature of that tidal interaction that pulls things together. So even before he gets inside the event horizon, he gets stretched and squeezed. By the time he would get to the event horizon, he would be narrower than an atomic nucleus size. He would be narrower than that. And by the time he fell through the horizon, the sizes of all his matter would be extraordinarily small indeed, possibly even as small as the Planck length. And we see way in the background, far, far, far away, not being affected by those tidal forces, is Jill in her spaceship maybe 300,000 kilometers away. And just to make sure that everything was normal, she also dropped a beach ball, and that beach ball got shredded, but had Jack seen the beach ball, he might not have jumped out of the spacecraft. Well, they had a bad time, apparently, going on that rocket trip, and she somehow convinced him to jump into the black hole, whatever that's about. Don't really know, but that's interesting. Anyway, so gravitational lensing is another effect that can occur, and we saw that, and that was the effect that we saw of all the light. The path of the light is being bent and redirected by the curvature, not the gravitational field, but by the curvature of space-time that is created by the concentration of mass as a black hole. So the observer is that kind of triangular eye thing on the left, and the black hole would be this reddish thing that's in the center, and we might have multiple images. And the light that comes from the object, which is actually the real object, the light would come from the top of the object, and it could be redirected to above and below. So you could actually see multiple images of an object above and below. The same object could be seen above and below a black hole because of the redirection of light by the curvature of spacetime. So curvature of spacetime can act as a lens and actually bend the curvature of the direction of light, and that's actually seen in, say, the deep gravitational fields of massive galaxy clusters such as this one. And this galaxy cluster has numerous arcs and curves in the background, and each of those is a gravitationally lensed galaxy far, far, far in the background. We can see this in a much more entertaining fashion. It's again by Dr. Andrew Hamilton, and what he did is he created a simulation where we pretended that the Earth is orbiting a black hole with a mass of 2,000 times the mass of the Sun. And we're going to pretend that this Earth somehow can orbit at 3 times the Schwarzschild radius. Now it looks closer than 3 times the Schwarzschild radius, but that's because the gravitational curvature has actually bent the light around so that we can barely see anything. But there's some features that we see as the Earth orbits, and it's not that the Earth is getting stretched and pulled. Remember, if you're on the surface of the Earth, the equivalence principle says everything's normal. It's just distant observers see something really weird, and we're distant. Everybody on the Earth, well, if they could survive the tidal forces, which of course they can't, but pretend they can, it's like super duper duper Earth and it's surviving it. There's a couple things that we see. The first is that as the Earth is on the right-hand side, it's going away from us. And so we have a redshift and a time dilation of going slower as it's orbiting. And when it's approaching us on the left-hand side, we see it's blue shifted, so it is a bluish tint as the light gets blue shifted as it moves towards us because of the rotation aspect. The Earth at this point would be orbiting approximately 80 times a second. So that's where that redshift and blue shift is coming from. And the distorted view of the Earth as it goes behind the black hole is the gravitational lensing due to the redirection of light that's reflected off of the Earth and comes to us from that source. So this shows multiple things: the gravitational redshift, the time dilation as it orbits, as well as the distortion due to of light's path as it orbits a massive black hole such as this. So that's what we call an Einstein ring, and the Einstein ring is a perfect example of perfectly aligned something in the background. We see that white image in the background. Maybe there's a bright star or an extended object, and it's perfectly positioned so that the light gets redirected in a ring, and that's what we call an Einstein ring. Now, if we orbit a black hole, we can then say, let's get really close and orbit a black hole, and there's an unstable circular orbit, not a stable circular orbit, but an unstable circular orbit at 2 times the Schwarzschild radius above the surface. So 3 times the distance from the singularity at 3, then that's the last stable orbit. And what we find is that if you're at this location, if there's a supermassive black hole like we find at the center of Milky Way, it would take about 10 minutes to orbit at this height. But in this unstable orbit, if you turn on your jets just a little bit, you can either go up or down, and any motion at all would send you either careening into the black hole or spiraling quickly outward, any tiny thrust. And there's also a weird element. Those kind of 2 poles are really, we actually are seeing the north and south pole of the black hole in our view. And if we got even closer, we would actually see the entire surface of the black hole, the entire event horizon, all at once. And that's when we are actually passing through the event horizon, is when we see the entire thing at once. Now, if you orbit the black hole at the speed of light, and you're right at nobody can travel at the speed of light, but if you're orbiting at the photon sphere, which is 1.5 Schwarzschild radii, then this is what you'd see. So this is the view of a photon as it travels at 1.5 times this 1.5 Schwarzschild radius over a black hole. Again, this is from Andrew Hamilton's website. And if you just fall in, this is what Jack saw as he fell straight in. As he looked up and fell straight in, the universe above him actually shrank. Notice it got dark around it. So he had a full sky view, and that full sky view shrank and shrank and shrank, got bluer and bluer and bluer, brighter and brighter and brighter, and more and more intense, until all of the light of the universe were coming down to him from a single point of infinite intensity. And that infinite intensity is as he is falling through the event horizon. So that's what you would see if you just looked straight up and fell straight in. There would be infinite blackness around from where light could not reach you, and it would get darker and darker and darker, and your view would get smaller and smaller and smaller with all light coming from one point. So what's inside a black hole? No one knows. No one knows at all. There's nothing to know. It can't be known because there's no way to understand what goes on. However, we can make metrics, and we can make space-time metrics or measurements of space and time inside of there. That would, but likely what happens at this point, the understanding is that the mass collapses until it has 0 radius and the density becomes infinite, which is kind of weird, but it's inside of an event horizon, so we'll never know really what happens. We have no idea what happens. Might be something that stops it. Maybe it actually doesn't reach the singularity. Maybe nothing ever does, because everything below it is still falling at faster than the speed of light towards it. Now, this is all pretty crazy and everything, but let's think of a new way of talking about it, which is what Dr. Andrew Hamilton likes to propose. He created a model of black holes, which is very interesting and helpful to understand, so you can really get a conceptual understanding of black holes. He called it the river model. So we can think instead of having curvature of spacetime, a totally mathematically equivalent way of thinking is to think of a flat spacetime where space is rushing, where space itself is moving towards the singularity, and everything is trying to rush against that. So we can think of photons as our fishes, and the fishes are rushing against it. But if the waterfall of space is going at the speed of light, well, then the fish that's a photon can't go up that thing anymore, and it gets stuck and it gets carried down. And inside the event horizon, then it's too fast. So here's what we mean is that the event horizon, those arrows show the rate at which space is flowing towards the singularity, and it's falling in free fall towards the singularity. Space itself in flat space-time. We can pretend now that space is not curved. Rather than say it's curved, we say it's flat, but that's flowing. So if we then think of a flowing flat space, and each of those arrows represents the escape speed, or the other way is the free fall speed. So that is the speed at which space is flowing, and once it reaches the horizon, it's flowing at the speed of light. So inside the horizon, the space itself is flowing towards the singularity faster than the speed of light, so therefore nothing can go faster than the speed of light. Space can go faster than the speed of light, but no thing can, and space is not a thing, so therefore it can go faster than the speed of light. I'll let you ponder that little bit for a while. And the idea is that nothing, since nothing can go no thing, no light can go faster than the speed of light, therefore the space-time flow overwhelms the flow of things and carries it down like a river. And so that's a mathematically equivalent way to the Schwarzschild metric. And that's a very easy way to think about it. And it's exactly equivalent to what I'm about to show you, which is the Schwarzschild metric. This is the way we measure space and time inside and near some sort of black hole or a spherical object. What this equation means is that we have, let's just look at the pieces. The little thing on the left-hand side, ds squared, means that's the actual physical length squared. So it's derived from the concept of the length of a triangle in Pythagorean theorem, where the hypotenuse squared equals the sum of the two sides squared. But now we take it in terms of a curved space-time. We're going back to curved space-time, away from the waterfall concept, back to Karl Schwarzschild metric from the 1930s, and we see 1917, and we see that there is a term that describes time, which is dt squared, which is a square of a tiny interval of time times the speed of light squared, and then you multiply it by that funny factor in front. And then we have dr squared, which is a tiny interval of radial distance from the event horizon up, and that's divided by that funny thing. And then we have the d omega squared, which shows that we're going to move left and right a little bit, maybe not up and down, but left and right and back and forth with respect to the surface, the event horizon itself, at some distance. So this is our way of measuring the shortest distance between two events in space-time. And as we use this thing, the actual distance is the ds squared. That's the physical distance. But each of the dt, dr, and d omegas are coordinate distances. They're not distances, they're the coordinates that are measured locally by, say, Jack as he falls in, or Jill as she's far away. But when we want to say, well, how far is Jack from Jill, then we are measuring ds squared, and we have to sum up all the little tiny bits to see how far he actually is. Well, let's actually make it a little easier for ourselves and pretend for a while that gravity is weak. So we go back to our energy equation, mp squared equals gm over r squared, and let's assume that we then say that v is now the speed of light. So if the gravitational potential energy is much, 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 much less than the rest energy, or the E equals mc squared thing, then gravity is weak. And we can transform the other equation in the previous equation into the one we see here, and that we can play with this thing and say, what does it take in order to make a satellite orbit the Earth at a fixed radius above the equator? And we can actually use this equation to derive the classic standard equation of the speed of a circle is equal to gm over r. You can use the equation above by saying that it's at a fixed distance, and it's going at a fixed circular speed. We're just going to assume that, and use this equation, this metric, this way of measuring space-time. And then once we get a relationship, we can say, now pretend you kick it a little bit above or outside that orbit just a little bit. And we find that that is the shortest possible distance in space-time is to make a circle. And that circle then is what we call a world line. And then we can derive rather rapidly from this concept of just kicking it a little bit and saying, a little bit longer, a little bit shorter. Can we actually make it shorter or longer? And the answer is you can't. And once you do that, then you derive from those concepts and using this metric the speed of something orbiting in a circle above a planet of mass m of at height r. And that's what that means. And that's good to know because general relativity has the solution of the Schwarzschild metric, which then we can use to derive Newton's laws. So all of Newton's laws of gravity are actually inside that middle equation. They're just hidden in there, and you just have to solve it using conditions and concepts, and you can derive everything else. So all of Newton's laws of gravity and motion are put inside this measurement of space-time that we see in the middle. Now there is something really funny I should want to highlight to you, is that gm over cr squared, which is really kind of funny, because if we look closely, inside the parentheses, you've got 1 minus that quantity. And so what is the 4 things? You got the 4 things are a 2, it's just a number, and g is Newton's gravitational constant. M is the mass that's doing the thing, that's gravitating. C squared is the speed of light squared, and r is the distance away from the event horizon of a mass of m, which is interesting. Away from the surface from it. And that's fascinating because g is a number and c squared is a number, but mass is a measurement and r is a radial distance. So somehow we're converting mass into length. Let's see what that really means. If we then say, well, mass has to be converted into length, so g over c squared is actually a conversion factor. And that's how we convert. Actually, I forgot the number 2 in there, so let's just throw in what's the number 2? Yeah, let's put a 2 on top. So 2g over c squared shows how you convert gravitational energy of mass into a length. So we just simply divide the one by the other, and we find that the conversion factor between meters and kilograms is that there are 7.416 times 10 to the minus 28th meters in a kilogram. That's a weird thought. Well, if you have a lot of kilograms, then that length becomes large. And then we say, well, let's say we have 10 to the 30th kilograms. Oh wait, that becomes about 1,000 meters, which is the Schwarzschild radius of the sun. So we can actually derive from this concept that mass is actually a length. Funny thing to think about. So we can then think of mass as being a length, so another interpretation of that is space is actually longer near massive objects. And since space is longer near massive objects, it wouldn't be like dimpling into some other place, it's just simply bigger. And the way we can think of it as being bigger is that those grid marks are coordinate marks. Think of it as a topological map that you might use going up and down a mountain when you go hiking. And so those grid marks display, if the grid marks are close together, then you know that you're going up and down a very steep hill. But if the grid marks are far apart, which is kind of what we see in this image, it's kind of like it's been stretched, then if they're far apart, then there's no hills there. Or if they're regular, way out at the edge, they're regular, and there's no hills or bumpiness. But what we could have done with this thing is just put all the grid lines really close together. They would be squish together inside of this image. Instead of making a dimple, just have them compressed together into a point. And if they're really close together, then space has been stretched, and therefore it's been made longer in those areas. And another way to think about it then is that we can again bring back our concept of the way space is flowing, we can think of space as flowing and it's carrying the mass along with it. And mass is the thing that also makes the direction from which it flows. So mass affects the flow of space-time in the river model, but it also in the curvature model, which are this exact same way of thinking, just slightly different words, is that the mass tells space-time how to move, and space-time tells mass how to move, and mass tells space-time how to curve. So the dimple of space-time is created by mass, and then the mass then says, oh, I made a dimple, I got to follow the dimple. And so as it moves, it must orbit in a dimpled sort of shape. And that's a classic concept that was coined by Wheeler in his textbook. And so that's the way we can best think about space-time curvature and its interrelationship. Well, how can we see black holes? Well, what can we see about black holes? If they're black, how do we hope to see them? And we look for their gravity on their surroundings because we're looking for maybe a star orbiting something that, well, isn't there. Or maybe there's a huge amount of X-rays that are being emitted by gas as it falls into a black hole. And that's what we call X-ray binaries. An X-ray binary is a bright source of X-rays that can be seen by something like the Uhuru satellite or Chandra X-ray Observatory or the Fermi Space Satellite or even the New Star Observatory. And let's say you have a spectroscopic binary, which is a star that has emission lines and it's moving back and forth rapidly, and the other one's invisible. And maybe you find that the mass that it's orbiting is very large. Or and therefore it might be really close if they're spectroscopic, and the visible star dumps mass on the companion, and as it dumps mass on the companion, the gas gets hotter and hotter and hotter until it emits X-rays, and that makes an X-ray binary. And you can by looking at the orbital parameters as well as the flickering of the X-rays, can give you the parameters and size of the black hole. And so if you find a black hole candidate, you're looking for something where the mass is about 3 times the mass of the sun. So what are some candidates? They have to be bigger than 3 times the mass of the sun, and that means it would be too big for a neutron star. And there are about 20 or 50 or so, more than that. There's about 50 or 100 confirmed black holes candidates, and I'll post those. There's a definite little list of black holes in like a Wikipedia that continually grows. So I have an out-of-date slide here. So here we go. But the first one to be discovered was Cygnus X1. We're going to take a look at that as a mass of 14.8 solar masses, but most black holes are between 4 and 10 solar masses, except for the really big ones, which are billion solar mass black holes or million solar mass black holes. Actually, our galaxy, well, there's 1 billion or so stellar-sized black holes in our galaxy, because there's a lot of iron in our blood, and that came from the supermassive explosions of stars as they've exploded. So we got to figure out where they're at. And then what are the observational evidence? Well, we're going to focus on Cygnus X1. It is the brightest, one of the brightest X-ray sources in the sky, and it's in the constellation Cygnus, and it's probably the first thing that was accepted to be a black hole. It was discovered in 1964, and we know now with measurements that its mass is about 14.8 solar masses, and its distance is over 6,000 light years. Now, the reason that we think it's too small is because it was because of how fast the X-ray bursts come. So if you have a millisecond X-ray burst, that means it can't be larger than 1 light millisecond, which is 300 kilometers. So the largest event, the event horizon, must be smaller than 300 kilometers. Therefore, we think that something really small, that event horizon of 300 kilometers, is the outer limit for the event horizon. So that's where the X-ray bursts are coming from. So they have to be falling in before then, but there isn't anything past those X-ray bursts. So they kind of fall in and they're done. It's not like there's a massive burst that occurs and there's just these little tiny bursts that go pop, 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 pop. And it's not like there's something that glows in X-rays as though it's glowing from the surface of something like a neutron star with its massive X-ray binary output. For a black hole to be 14 solar masses, the star that made it had to be about 40 solar masses. And there's no supernova remnant around there. So we think that a 40 solar mass star would have simply collapsed directly to a black hole at the end of its life, which is a wild thought for its exiting strategy. Finally, we know that X Cygnus X1 is in a high-mass X-ray binary system, and we know that their separation is about 1/4 of an astronomical unit, which is closer than Mercury orbits the Sun. So we got something 14 solar masses, and another object that's somewhere between 20 and 40 solar masses, and they're orbiting at a distance that's smaller than the orbit of Mercury. So you're going to get a stellar wind as the big O and B type blue supergiant, which has been observed, dumps material onto a companion accretion disk around the X-ray source. And as it gets closer and closer and closer, it gets hotter and hotter and hotter, and the inner accretion disk gets to be millions of degrees, and as some of that material goes out into jets, but those jets aren't observed with respect to this, but it's posited they exist, and a significant fraction of it, that's where we see the X-ray burst, is material just falling into the center of it. And there's a periodicity of about 5 or so days, as they zip around as they orbit in about 5 days. Now the whole system itself, this pair, seems to belong to a stellar association of O and B type stars called Cygnus OB3. And if it's part of that organization, then the whole thing is about 5 million years old, which is where we get the concept of the masses of both of that star, and why we think it has to have that mass. Because if the whole association is 5 million years old, then it had to have evolved fast, and it had to be about 40 solar masses in order to evolve that quickly. So let's take a look at where it is in the sky. This is the location of Cygnus X1 in the sky. This is the location of Cygnus X1 in the sky, and you can actually see the star in there. And if it's zoomed in, we can, in theory, zoom in. There's an image by the Chandra X-ray Observatory, and the X-ray observations. This is the X-ray image of Cygnus X1 taken by the Chandra X-ray Observatory as they orbit each other every 6 days or so. And we see that it's actually kind of big. It's about 1.5 arc minutes. Remember, the moon is about 30 arc minutes across. So this image is about 1/10 of, half of a tenth is about 5% the diameter of the moon. So it's like the same size as a relatively large crater that can be seen with telescopes on the surface of the moon, or small telescope or binoculars on the surface of the moon. So that's how big this image is. It's about the size of a large crater seen through binoculars on the moon. So if you had X-ray eyes, you could see it, and you'd actually be able to make out its size. Furthermore, we know how we study to find its size is by looking at the X-ray spectrum. So the Chandra X-ray Observatory is able to actually get the spectrum of light, and we find that it has a bright emission feature that would be due to iron falling into the center of it. Now, if it gets hot enough to emit X-rays, then it's dense enough, the gravitational potential energy is dense enough for it to actually become, to do some nuclear fusion close by. Actually, it's mostly heat and friction that would do the trick, but there would be iron nuclei, and those would emit enormous amounts of X-rays. And the width of that emission line, that bump up, not the spike in the middle, that's where the main emission's at, but there's a width to this line, a very large width, and that's because it's being gravitationally redshifted and blue shifted as it goes around, and it's broadened because of gravitational redshifting and the Doppler effect of zipping around in a disk. So here's what we think that the Cygnus X1 probably looks like, with that bright O and B type supergiant next to it, dumping material as it gets just to the balance point where the pull of the 14 solar mass black hole is greater than the pull of the 40 solar mass blue giant, and it falls from the blue giant into the disk. There's a hot spot where it contacts the disk, and the material rotates and rotates around until it finally falls into the black hole. And you actually can't see the black hole. We see a black area, and that is not where the black hole is. Remember, a black hole of 40 solar masses, that's only going to be about 30 kilometers. And remember, a typical star like this is going to be a star like the blue supergiant over there. That's going to be bigger than the sun. So remember, go back to our scale size thing we did at the beginning, and you actually can't see the black hole there. Even that dark spot would be invisible. So the X-rays are being emitted even tighter there, so this artist concept is still flawed. We'd have to get very, very, very close in order to actually see the event horizon, or even get close enough to see it. And there would be jets that would be coming off of it, And because of this formation of material falling into a black hole, Cygnus X1 is called a microquasar, and we'll see what that means when we talk about galaxies in the future. Funny enough is we can go also and discover other things about black holes. The movie Interstellar had the most accurate depiction of the appearance of a black hole, and they did a massive supercomputer imaging of what a black hole would look like. And so there's a spaceship kind of floating around next to a black hole, Gargantua, a very supermassive black hole with a disk around it, and that disk is around it, but we see it apparently above and below because of the gravitational lensing of the material around it as the spaceship goes around. The movie Interstellar was designed to actually try to show a black hole in its most accurate depiction that was ever done in any Hollywood feature. So this is a relatively accurate portrayal. There were some Hollywoodish features, like we didn't get rid of, there would be certain squarish features to it, as well as lots of redshift and blue shift, so you'd only see one side of it at a time. But it's Hollywood, so they had to do some stuff. Anyway, so look up Kip Thorne and Interstellar to see more about that. Also, we can learn about different kinds of black holes. There's one at the center of our Milky Way, and this is from the European Southern Observatory looking directly at it. And there's a supermassive black hole at the center of our Milky Way that's about 4 million times the mass of our sun. And we know it's there because of the effect of stars that are around it. And Andrea Getz's group at UCLA has been studying this for over a decade, over 20 years, looking at individual stars moving in their orbits around the central supermassive black hole in the center of the Milky Way, and is deduced by the motions of stars over the course of 20 years that are moving incredibly fast that there is something really big there, about 4 million times the mass of the sun, and it would be about the size of it would be comparable to the size, something about the size of the inner solar system. But that's 4 million solar masses of black hole. Next, we go to the outer skirts of the cosmos, and remember there's a jet coming out, so where there's huge massive jets emitting X-rays from distant galaxies, we can expect that there's a supermassive black hole in this galaxy, M87, and M87 as its jet appears in radio frequencies, and it emits this crazy jet, and that is also the result of a supermassive black hole, material falling into that black hole and spiraling around magnetic fields and being ejected out into intergalactic space. But black holes aren't really black. General relativity says they're totally black, but that doesn't take into account quantum mechanics. And quantum mechanics says some really interesting things. Quantum mechanics, according to, if you pull that in, Stephen Hawking posed that in the severe gravitational field around a black hole, the amount of gravitational energy of the gravitational field is so great that it can actually create subatomic particles and light. And as it creates them, one particle could fall into the black hole and its antiparticle could leave the black hole. And if that happens, it's emitting particles. And that can be considered thermal radiation because that would be at a particular temperature according to the size of the black hole. So the smaller the mass, the hotter it would be, and that's what's called Hawking radiation, and therefore it would be a faster evaporation. But if for black holes that are big, like normal things, it would be very, very, very tiny because a solar mass black hole would take 10 to the 64th years to evaporate. Well, the universe is only about 10 to the 10th years old, so that's about 10 to the 54th times the present age universe. And Hawking radiation is a very interesting concept. It's most likely incredibly unimportant for today, but it will be an important process for the production of light and energy at the distant future of the universe. So what kind of black holes are there out there in the cosmos? Well, once we get to things that are sized white dwarfs and neutron stars, there are stellar-sized black holes, there are supermassive black holes, but intermediate mass black holes between, say, 100 times the mass of the sun and less than 1 million times the mass of the sun, they're rare. Stellar mass black holes seem to be extraordinarily common, and they're easy to make by making supernovae explosions of 40 solar mass black holes. Well, it's not easy to make, but at least that's commoner than intermediate mass black holes. And supermassive black holes are in the center of pretty much every galaxy, and there are at least 1 million solar masses. But determining the intermediate mass solar mass black holes, that's a puzzle that's currently out there among all of astronomy, and nobody really knows what's going on with that. So that's a lot about black holes, and they're really fascinating objects, and we'll be talking more about them next time. See you soon.